This question is from GATE 2021 Mechanical Engineering paper, Set 1, question number 30. Consider a 2 degree of freedom system as shown in the figure, where PQ is a rigid uniform rod of length B and mass M, which is small m. Assume that the spring deflects horizontally. Force F is applied horizontally at Q. For this system, the Lagrangian L is. Let's find out. Lagrangian L is nothing but the difference between kinetic energy of the system and potential energy of the system. So if we manage to find out both of these energies, we can find the Lagrangian. Kinetic energy for the system will be given as the sum of kinetic energy of the mass capital M, kinetic energy of spring, and kinetic energy of the rod. So for each of the component, we have taken their kinetic energies and added up together to find out the kinetic energy of this complete vibrating system. Now here we know that kinetic energy of spring can be taken as 0, because for a spring we assume that when it deflects, it stores the potential energy by virtue of its configuration. Then we have the potential energy of the system. In similar manner will be the sum of potential energy of the mass, potential energy of spring, and potential energy of the rod. Now in this case, potential energy for the mass M will be 0, because if we consider this is the datum, potential energy of this mass, its center being at the datum, will be 0. While for rod and spring, it will be a non-zero value. So let's find out each of these energies and then add them up. So we have the first component, kinetic energy for the mass capital M. This is given as half into the mass capital M into its velocity square. Its velocity can be written as x dot because the displacement is x. So velocity will be x dot, derivative of x with respect to time, square of it. Second, we have kinetic energy of the rod. Kinetic energy of the rod, as it is undergoing rotational motion along with the translational motion, will be given as, by virtue of the rotational motion, it will be half into its moment of inertia about the point of rotation, so about P, into its angular velocity square. This is the rotational kinetic energy, and translational kinetic energy will be given as half into mass of the rod into velocity of the center of mass, and this velocity is written as displacement of the center of mass dot, which is nothing but time derivative of the displacement of center of the mass of rod. Now we know that center of mass will be located exactly at half of the length of rod because its mass is uniformly distributed. So we can take this height from the datum. This height will be b by 2 cos theta. So it is d center of mass, that is displacement of the center of mass dot, square of it. Now we need to find these two components, moment of inertia of the rod about point P and velocity of the center of mass of the rod. So I of the rod about P can be given as moment of inertia of the rod about its own center of mass will be m length square, which is b square by 12. This is a standard formula for moment of inertia of a rod, plus mass of the rod into half of the length of rod b by 2 square of it, because distance between center of mass and point P, which I have marked it here with the white arrow line, is b by 2. This I have written using the parallel axis theorem. So this turns out to be mb square by 3. Now we need to find out velocity of center of mass, which will be equal to, we can write the displacement of the center of mass as x, the translational displacement, plus this rotational displacement will be this much distance. For the center of mass, we have to take it as b by 2, which is this length, into sine of theta, because this is the opposite side. So we have b by 2 sine theta, and we have to take time derivative of this whole term. So dot. We take the time derivative, we have d dot center of mass will be equal to x dot plus b by 2. Derivative of sine theta is cos theta, and derivative of theta we will have to take by chain rule. So it is theta dot. We need to take square of this term. So let's do that. We'll directly write it here. Kinetic energy of rod will be equal to half into mb square by 3 into omega can be written as theta dot. So we have theta dot square plus half into m into this whole term bracket square can be expanded and written as x dot square plus 2 times x dot b by 2 cos theta theta dot plus b by 2 square of this term cos square theta theta dot square. So this is the complete term. It's pretty long, write it carefully. But in here, we know that theta will be a small displacement and therefore when theta is almost equal to 0, cos theta will also be approximately equal to 0. So this term can be considered 0 for small values of theta. So we are left with this complete term that we will substitute later in the formula for Lagrangian. Third one, we need to find potential energy of the spring. This simply will be half into its stiffness k into its displacement, that is x square, half k x square. Then we have the last one, potential energy of the rod. Now for potential energy of the rod also we will take the center of mass because its weight will have to be taken from the center of mass itself. So it should be mgh. We can write m into g is the weight of the rod into, now distance h is below the datum. This is the datum and therefore the distance when we take below datum, it will be a negative value. We have minus of the vertical distance is b by 2 cos theta. This has to be taken as the vertical distance, not the half length of the rod. Therefore we have taken b by 2 cos theta and not b by 2. This can be written as minus mgb by 2 cos theta. So let's put all these values that we have found out. I'll just highlight them. So this is the first term, this one's the second term, this one's the third term, and this is the fourth term. So all of these values we will put in the formula for Lagrangian appropriately with their correct signs and then find out the final answer. So we have L will be equal to half into, now we have two terms, half capital M x dot square and half small m x dot square. In each of the values for kinetic energy of mass m and kinetic energy of rod. So we can combine them together to write m plus small m x dot square plus, next term that we have is half into m x dot b cos theta into theta dot. This is the component that is coming from kinetic energy of rod plus 1 by 6 mb square theta dot square. This also comes from kinetic energy of the rod, the rotational component. Then we have minus of potential energy. So when we write minus mg by 2 b cos theta, we have plus mg by 2 b cos theta. And because it's minus half k x square, it will remain as it is. So that sign in the Lagrangian which we have for potential energy, the negative sign, that tags along here and we get the last term as a negative term. So this is our answer with 5 of the terms. Let's go back and mark the correct option. Option B is correct. To learn about Lagrangian formalism in detail, you can refer to the NPTEL video Module 1, Lecture 7, Lagrangian Formalism. It's from the course lecture series on classical physics. The course is taught by Professor V. Balakrishnan. He is from Department of Physics of IIT Madras. I hope this solution helps you clear your doubt. Thank you.